In this lecture, let's understand about the PendSV exception. It's an exception type 14 and has a programmable priority level. So the exception number is 14. This exception is triggered by setting its pending status by writing to the interrupt control and state register of the processor. You don't have any instruction to trigger a PendSV exception. You have to pend this exception in the interrupt control and state register of the processor. Triggering a PendSV system exception is a way of invoking the preemptive kernel to carry out the context switch in an OS environment. That's a major use case of the PendSV. If you are using some standalone application without any kernel or scheduling things, then you need not to use this exception. Majorly, it is used in an OS environment. So in an OS environment, PendSV handler is set to the lowest priority level, and the PendSV handler carries out the context switch operation. Context switching is one of the key operation in OS design. Scheduler does context switching. That operations are carried out by the PendSV handler. That's a major use case. Typically, this exception is triggered inside a higher priority exception, and it gets executed when the higher priority handler finishes. Using this characteristic, we can schedule the PendSV exception handler to be executed after all the other interrupt processing tasks are done, because generally we keep the priority of PendSV as lowest possible. That's the reason in an OS noisy environment, after all the IRQs are executed or finished, the PendSV handler will run. This is very helpful for a context switching operation, which is a crucial operation in various OS design, and using PendSV in context switching will be more efficient in an interrupt noisy environment. Because in an interrupt noisy environment, we need to delay the context switching until all the IRQs are executed. Context switching is delayed until all the active ISRs are executed or finished. Generally, that is a design thing which is followed in OS or scheduler design. In that case, we can use PendSV to carry out the context switching after all the IRQs are executed or finished. What exactly is a context switch? Context switch means saving the context of old task and retrieving the context of the next task which needs to be scheduled on the processor. Let's consider a scenario of multiple tasks. There are two tasks, task A and task B. Task A is currently running on the processor. After some time, you want to remove this task A from the processor, and you have to schedule task B. For this, you can use a scheduler. What you can do is you can make a scheduler to run at constant or fixed duration, let's say 1 millisecond. For every 1 millisecond, the scheduler code runs. This is actually a kernel code, or it is a code which is part of the kernel. So the scheduler runs for every 1 millisecond. Let's assume that. When it runs, what it does is it saves the context of the currently running task onto the stack memory, and then it retrieves the context of the next task which is in the ready list. It makes that task to run on the CPU. Here it saves the context of old task, and here it retrieves the context of the next task which is going to run on the processor. This operation we call it as a context switch. That is generally carried out by the scheduler. The OS code runs on each SysTick timer exception and decides to schedule different tasks. Let's understand the scenario of PendSV in context switching. So one possible scenario how you can use PendSV in context switching. Let's say you have a task or user task running in the thread mode. That's the thread mode code. And a sysdig timeout happens. Now it's the time to run the scheduler. Scheduler runs. Scheduler code is nothing but a sysdig handler. What scheduler code does is it pends the PendSV. It doesn't carry out context switch actually. I will tell you why it doesn't carry out the context switch. I mean, it can carry out the context switch, but generally we don't do context switch in the timer handler. The sysdig handler or the scheduler just pends the PendSV. When that sysdig handler exits, if there are no interrupts in the system, then PendSV handler runs because PendSV exception is configured for the lowest possible priority. So if there are no active interrupts, then PendSV will run. In the PendSV, context switch will be done. Context switch means context of this task will be saved to the stack and context of the next task will be retrieved from the stack. And PendSV handler schedules or it makes the next task to run on the CPU. The task B executes. When task B is executing, some other interrupt happens. Let's say a button interrupt or a peripheral interrupt. The ISR executes. ISR is a handler code. It can always preempt the thread mode code. Now ISR is executing and suddenly what happens is this timeout happens. That is sysdig timeout happens. Sysdig will preempt that ISR. This is the interrupt nesting. This is a time where the timeout happened. This is a fixed interval timeout. Whenever sysdig times out, scheduler runs. When the scheduler runs here, and it again pends the PendSV, just pends the PendSV and exits here. When this scheduler exits, this ISR continues here. When ISR finishes, ISR exits here. And when this ISR is finished, the PendSV handler will be invoked and it will carry out the context switch. Here you can see that the context switch didn't delay this ISR execution, isn't it? You can consider this as an interrupt noisy environment. There is an interrupt actually. But the processing of that interrupt is not delayed by the context switch because when the scheduler ran, it just pends the PendSV. It didn't do any context switch. It immediately returned to the ISR. After ISR is finished, the PendSV invoked and it does the context switch. That's why when all the interrupt service routines are finished, then only PendSV handler will be invoked and context switch will be taken care. After that, task A continues. That's the use case of PendSV, how you can use in context switching operation. In the previous animation, I said that we generally don't do context switch in the sysdig handler. We always do that in the PendSV handler by pending the PendSV in the sysdig handler. This slide explains the scenario of context switching without PendSV. Let's say you have a task here. Task A is executing and sysdig timeout happens. Sysdig handler runs. You do the context switch here itself. Of course, you can do that. When you do that, what happens? Task B is scheduled. You do all the scheduling thing, that is saving the context of task A and retrieving the context of task B, everything you do in this sysdig handler. If you do that, then task B resumes here. Task B is running and interrupt triggers. Some interrupt. As I said, it could be a button interrupt or a UART interrupt or whatever it is. And the ISR runs. ISR is unfinished or it is just executed half. Here, the sysdig timeout happens. Now again the scheduler runs. When the scheduler runs, according to your design, you do all the context switch here itself. You do the context switch here. That means you retrieve the context of the next task and you make that task to schedule onto the processor. What is a task? Task is a thread mode code. That means you are attempting to come to thread mode by keeping an unfinished ISR. This is a fault that is not allowed in ARM Cortex-MX processor. You cannot return to thread mode by keeping unfinished handler code, that is, in this case, some ISR handler. That's why processor will not allow you to come to thread mode. Rather, it rises a fault. So the exact fault is usage fault. That's the reason why we don't do context switch operation inside the SysTick handler. Rather, we postpone it to the PendSV handler. The better technique is, instead of doing context switch here, just pend the PendSV. Then execute the ISR, and then when ISR exits, PendSV runs and it does the context switch. Let's understand some other use cases of PendSV. You can use PendSV for offloading interrupt processing. If a higher priority handler is doing time-consuming work, then other lower priority interrupts may suffer, isn't it? And system's responsiveness may reduce. This can be solved using a combination of ISR and PendSV handler. Offloading interrupt processing using PendSV. Interrupts may be serviced in two halves. So the first half is the time critical part that needs to be executed as a part of ISR execution. Second half is called as bottom half, is basically delayed execution where rest of the time consuming work will be done. So PendSV can be used in these cases to handle the second half execution by triggering it in the first half. You have a task A running. Let's say an interrupt triggers, and let's say IRQ0 and ISR of the IRQ0 runs. It's supposed to do some time consuming work. If it is keep doing time consuming work, then other interrupts may get delayed, right? Other lower priority interrupts may get delayed. What it does is, it does the first half processing, that is time critical processing in ISR 0. It just finishes time critical work in the ISR. Then it just pends the PendSV and exits. In that case, what happens is, when there are no active interrupts or when there are no active ISRs executing in the system, PendSV handler will run and it can carry out the non-time critical bottom half processing. That's how you can process the second half using the PendSV. That makes this ISR very short, isn't it? It does the time critical thing, pends the PendSV and exits. When PendSV runs, it does all bottom half processing. When it is doing any bottom half processing, if any interrupt triggers, that interrupt can preempt this PendSV, because PendSV is always configured for the lowest priority. IRQ1 in this case can preempt this PendSV and ISR1 can run. When this finishes, again PendSV resumes. When PendSV finishes, it can return to the thread mode. Here you can see that the work of the ISR is stretched up to here. It allows other ISRs to run in between. That's another use case of PendSV, which is used for offloading interrupt processing.